Inductance 2. Finish the right side of each equation. Voltage drop across a resistor, I times R. Voltage drop across a capacitor, Q over C. We've talked about those in previous videos. This last one is a new one. The voltage drop across an inductor is equal to minus L di dt, where this L is the inductance right there, and that is in henries. That's the unit that we use for inductance. And I believe it's capital L for inductance in honor of Lentz, of Lentz's law's fame. I think I heard that somewhere. Why is there a negative sign in that answer? There's a negative sign there because the EMF in the inductor is directed so as to oppose the change in the current. That's why there's a negative sign there. If an inductor has an inductance of 4.0 henries, it means that at the instant the current is changing at the rate of, say, 1 amp per second, then the induced EMF in the inductor at that instant is 4 volts. So that's what an inductance means. When we have a certain inductance, if the current is changing at the rate of, let's say, 1 amp per second, then the induced EMF is going to be in volts equal to the magnitude of that inductance. Let's do a couple of examples here. We are assuming again that we have a 4 Henry inductor, and we want to determine the induced EMF in that inductor for each of these given changes in current, instantaneous changes in current. And we also want to circle if the induced EMF is attempting to buoy up, that is support, or if it's attempting to hold down the current at that instant. If the current is changing at that rate, at that instant, the induced EMF will be 2 volts, 0.5 times 4. And since the current is on the increase, you can see that some of these, for example, number 2, you see there is a negative sign there. So that means the current is dropping. But in number 1 here, the current is increasing. And so this EMF in the inductor is going to try and hold down that changing current. If the current is changing at the rate of 3 amps per second, then the induced EMF has a magnitude of 12 volts. And here the current is dropping. And so the EMF is going to be directed so as to try to prevent that drop. Similarly, for number 3, the current is dropping at that rate. And for a 4 Henry inductor, that means that the EMF is going to be 1 volt, 0.25 times 4. And if the current is dropping, the EMF in the inductor will be trying to prevent that drop by buoying it up. A couple more. How about number 4? There's the rate of change of the current. In fact, we can circle buoy up or hold down right now. We can see that the current is on the increase. The EMF is going to try and hold it down. With how many volts will it oppose that change? 0.75 times 4 is 3. How about here? 8 volts. The current is on the increase. We're going to try and hold it down. How many volts? 4 times 4, 16 volts. And the current is dropping off. You can see it's dropping off rather rapidly. The inductor is going to do what it can to try and buoy that up. It is, of course, ultimately unsuccessful, but it prevents that change from happening quite so rapidly. Each of these attempts, buoying up or holding down, in the end fails. But the fact that those happen mean that the current in the circuit won't change as rapidly as it otherwise would have, which gives sort of a stabilizing effect